Hey Geometry, lesson 15. So we've been talking about similarity, and I told you we were going to talk more about triangles. Well, here's the day. So today we're going to talk about the angle criterion for two triangles to be similar. It's a theorem, which we're going to talk about today. And let's get into it. So first of all, your sheet is blank, and it wants you to draw two triangles of different sizes with two pairs of equal angles. Well, I found some, copied them, and pasted them here, and it just made it a lot easier. And bam, everything's measured. The instructions say then measure the lengths of the corresponding sides to verify that the ratio of their lengths is proportional. Use a ruler, compass, or protractor as necessary. So I measured the lengths. I actually measured the angles too. So if you look, I have angle A is 74, which corresponds good enough to angle D, which I measured at 73. Mind you, I'm measuring with a protractor on my iPad, so I'm going to have some error here. It's not a piece of paper. And then the measure of angle B was 59, which corresponds to the measure of angle E, which was 58 degrees. If we remember, way back to the beginning of the year, we learned that the interior of a triangle, all of the angles sum to 180. So because of that, I can say that the measure of angle C is 47 without measuring it, and that's pretty darn close to the measure of angle F, which was 49 degrees. Now, we didn't actually answer this question yet, so measure the lengths of the corresponding sides to verify the ratio. Okay, we're going to move this question down. Well, I still need to answer the beginning question, so I just did a little bit of division. I'm assuming my triangle's getting smaller, so I did 2.7 divided by 4.4 and got 0.61. And then 3.1 divided by 5 and got 0.62. That's pretty darn close. And then finally, 3.6 over 5.7, 0.63. So we can say that, well, I measured the lengths of the corresponding sides, and I verified the ratio of the length as proportional. Okay, that is close enough. Cool. Are the triangles that I drew in exercise 1 similar? Well, yes, because the sides are proportional and the angles are equal or congruent. Why is it that you only need to construct triangles where two pairs of angles are equal but not three? I said in the last slide because the interior of a triangle always sums to 180 degrees. So if two are equal, the third is going to be equal. Why were the ratios of the corresponding sides proportional? Well, since the triangles are similar, goodness. Since the triangles are similar, we know the sides are proportional. And the angles are congruent. If they're proportional, the ratios are going to be the same. That's just how similarity works. It's the definition of similarity that we've learned and have been using for a few lessons now. Okay, I'm skipping questions 5 and 6, but 5 is, like, I'm going to skip 5, we're going to talk for a minute, and then I'm going to skip 6, and then we're going to talk for a little bit more. So I don't know why I included all that information, but it's all right. You guys know what I'm doing. let's talk a little bit about what we've learned. I'm just going to do a tad bit of review to make sure that we're all on the same page. So I'm going to push pause and write some things down, and then I'll talk about it. Okay, two things I want to point out. First of all, we know that two figures are similar when we can describe a sequence of transformations to map one figure to another. Those transformations would be the dilation and any series of rigid transformations. Also, since similarity implies properties about corresponding side lengths and angle measures, we don't have to show all three sides and three angles are proportional or equal, would be the sides and angles, to show similarity. We don't have to prove everything to show similarity. We just have to prove a few things, which we'll actually get into next. Oops. The theorem that we are actually proving is two triangles with two pairs of equal corresponding angles are similar. It's called the angle-angle criterion. Goodness. For similarity. Okay? And we can just say angle, angle, or AA, and it works perfectly well. If we think back to the angle side angle criterion for triangle congruence, we would need to show two triangles with two pairs of equal corresponding angles and the side in between them that is equal in length. Okay, if we do two angles with the included side, then we could say that two triangles are congruent. But now, since we're just doing similarity, we're just proving that two angles are congruent, which is actually the third is congruent too. And we're using that for triangle similarity. If you remember, when we were first proving triangle congruence, we could not use angle, angle, angle as a reason. Now you know why, because angle, angle, angle being congruent doesn't necessarily mean that the triangles are congruent. The triangles are actually similar. Here you see the triangles that I used in problem 1. So given these two triangles, I have the measure of angle A equal to the measure of angle D, the measure of angle B equal to the measure of angle E, and therefore the measure of angle C is equal to the measure of angle F because of the third angle of a triangle. So given these two triangles, we're just talking about the two angles being congruent. Let's show that triangle ABC is in fact similar to triangle DEF. Okay, the first thing we can do is just talk about the scale factor. So if we can show that triangle DEF is congruent to a triangle that is a dilated version of triangle ABC with a scale factor, then we can actually describe the similarity transformation. Okay, the set of transformations, the dilation, the other transformations to map one figure onto another. So let's first talk about our scale factor. To calculate our scale factor, we did that in the first slide. we have, let's just, I mean, we could take any one of these sides, right? Let's just talk about DE over AB. And that would give us our scale factor. And I believe that was 2.7 over 4.4. No, I think that might be AB. Yep, yeah, that was the right one. And we got an answer of 0.61. So since DE over AB equals the R, the scale factor, let's go ahead and dilate triangle ABC from center A by a scale factor of 0.61. Okay, and that's on the next slide, which we find right here. So 0.61 is approximately 2/3, and that's what you see here. We decreased, these are parallel. This is about 2/3, that's about 1/3. So now we just constructed a triangle, so that triangle AB prime C prime is actually congruent to triangle DEF. So we know that angle A, the measure of angle A is equal to the measure of angle D. So we know here that the measure of angle B is equal to the measure of angle B prime because they're corresponding angles. Because, as I said, these are parallel. Cool? Since we already said that the measure of angle B is equal to the measure of angle E, that's also equal to the measure of angle B prime, transitive property. So the important part is right here. So we just went to angle and angle. Now let's look at sides. We can also say that side AB prime is equal to R times side AB because of dilation, and therefore side AB prime is equal to side DE because of our dilation and scale factor. So what we just did was angle, side, angle. Okay, we just proved that triangle AB prime C prime is congruent to triangle DEF because of angle side angle congruence. Cool. The purpose of this whole slide, though, is to show you that I can map triangle DEF onto triangle AB prime C prime by a series of rigid motions. I could also map triangle DEF onto triangle ABC by a series of dilation and rigid motions. So that would be my similarity. Okay, remember similarity, I dilate things. Congruence, it's just rigid transformations, right? Therefore, since a similarity transformation exists that maps triangle ABC to triangle DEF, we can say that triangle ABC is similar to triangle DEF. So getting into an exercise, are the triangles shown below similar? Explain. If the triangles are similar, identify any missing angle and side length measures. I don't know if they're similar. Let's look. I think I need to do a little addition and subtraction to find out some angle lengths. Sorry, some angle measures. Okay, I found the third angles of the two triangles. Now let's look at our scale factor if we can. The smaller triangle, the side between 44 degrees and 52 degrees is 7. which would be the same as 28/3. That gives me 0.75. The 6 is between 44 and 78. 44, and that's the same as the 8. Also 0.75. There's actually no way for us to know, sorry about that, the third side, because I can't compare it, right? I know my scale factor, but I can't multiply one thing to get the next. So I didn't actually finish answering the question. Are the triangles similar? Yes, because of the angle-angle similarity theorem. And then if they are similar, identify, etc. So yes, they are similar because of angle-angle. Are the triangles shown below similar? Explain. If they are similar, identify any missing angle and side length measures. Let's see. Let's look at our third angle first. 95 plus 25. Here we have 60 degrees. I can already, they're not similar. I don't know why I'm still adding and subtracting. 61 degrees. No, because I don't have two angles that are congruent. So that doesn't work, does it? Number 9, the triangles shown below are similar. Use what you know about similar triangles to find the missing side lengths x and y. Looks like those lines are probably parallel. Okay, so first we need to sort of decide what the name of our triangles are that are similar. So I'm just going to label these. So we know that these center angles are equal because they're vertical angles. So I can say that triangle ADE is similar. It's an awful similar sign. Is similar to triangle, and I went ADE, so I'm going to go ACB. So we need to name the corresponding parts in the right order. Now we can figure out which sides are corresponding and figure out our missing side. So I can say that this side and this side are corresponding, and that will give me my scale factor. Oops, I'm still in highlighter, sorry. 4 over 12 is 1/3. That's my scale factor. So now I can use that scale factor to find out my other missing sides. Let's switch to a pen. So, oops. These sides are also corresponding. So 3.14 over y is going to be equal to the scale factor. Y equals 9.42. And finally, third side. So we've been doing small over big. So x over 16.5 is equal to 1/3. I'm just doing the cross product here. So 16.5 divided by 3 is 5.5. And we can't solve all the angles, but that's okay. The triangles are similar, so now we just need to match up the corresponding sides to figure out what all the measurements are. And number 10, the triangles shown below are similar. Write an explanation to a student, Claudia, of how to find the lengths of x and y. I'm going to verbally do that, which is fine. If we look at, I have, the triangles are in the right placement, so they are just similar in that order. Now we can figure out the scale factor. If I compare the green to the red, I'm going to have 3 over 9 is equal to, let's just say, 2 over 2 plus y. That's one way I can solve for y. And then I can go, for another one, I can say 3 over 9. I got 9 by 6 plus 3 is equal to x over 12. Since I started this whole color coding thing, let's fix my mistake there. Okay, let's solve for x first because it's the easiest. I'm going to do my cross product. 36 equals 9x, x equals 4. And let's figure out the other one. So cross product, 18 equals 6 plus 3y. 3y equals 12, y equals 4. Awesome. So I just needed to set up the right proportions and ratios to solve for my missing sides. Cool. So what did we learn today? We learned about the angle similarity. If two angles on one triangle are congruent to two angles on another, then the triangles are in fact similar. And we only have to check those two things. Everything else is good. So tomorrow we'll go through some practice problems and make sure we understand it. Nice work today.